All right, in this video, I'm going to go over the greatest common factor, or GCF, as we like to abbreviate. But first, I'm going to go over just factoring, just as a quick reminder of what factoring is. Factoring is reducing a number to the different combinations of prime numbers that multiply together to get that number. Prime numbers are numbers that cannot be divided out evenly by any other numbers. So examples of prime numbers. Let's give you the first few. 1, 2, 3, 5, 7, 11, 13. See, 4 are going to be divided by 2. You see, 6 can be divided by 2, 8, and 8 can be divided by 2, 9 can be divided by 3, 12. So all those numbers are not prime. I mean, of course, we can divide them by themselves. I mean, 13 divided by 13 is 1, but I mean, that counts. That is one of the combinations of numbers that we can multiply together to get 705. So I'll just write combos over here and just write 705 times 1. This isn't really factoring so much as it is finding how many different combos of two numbers multiply together to get 705. There is another combo that I can think of, because a negative times a negative gets you a positive. Negative 705 times negative 1 also gets you positive 705. All right. All right. Is 705 prime? No, not even close. You should recognize that in the ones place there's a 5, so we can divide it by 5. So 705. Don't want to use a calculator for this because that's cheating. 5 times 1 is 5. 5 times 4 is 20. Bring down 5. 5 times 1 is 5. Good. So 5 times 1, 41. There's another combo. 5 times 1, 41. And of course, negative 5 and negative 141. But I'm not going to write that one down too. I mean, I'd run out of room here. Now, let's try and find some more prime numbers. Is 141 prime? No, it's not. I can tell because if something is divisible by 3, its digits will add together to be something that is divisible by 3. 1 plus 4 plus 1 is 6. We can divide 6 by 3, right? So that means we can divide 141 by 3. It's a nice little trick. I don't know why that works, but it does. 3 times 4? No. Yeah, 3 times 4 is 12. Had a brain problem there. Bring down the 1. 3 times 7 is 21. Nothing left over. Good. That means it worked. 3 times 47. Now is 47 prime? Yes, I think this is it. But this isn't a combination of two numbers that multiply to get 705. No, 3 times 47, that'll just give you 141, right? We want to include the 5 here in our list of two different number combinations that get us 705. Okay, so we can combine these two, right? 5 times 3 is 15. 15 times 47, there's a combo. What's 5 times 47? Let's erase my little side notes here. 47 times 5, 7 times 5, 35. 4 times 5 is 20 plus 3, so that's 23. That should be 235. Check my math on that. I don't usually do long multiplication these days. Yeah, 235. Wow, I still got it. So there's another combo. 3 times 235. Because I combined this 5 with the 47, right? And that is all of them. We included the 1 times its, the number itself. And we have all the different negative versions of them. Let's just put positive, negative next to all of them. And that is what they want us to do when finding the greatest common factor. But this is just one number we're dealing with. It gets crazy when we're dealing with algebra, because then we have all these variables that come into place. Variables are easy to factor because you don't have to multiply and divide them out. You just, count the number in the exponent, and it works out fine. Okay, so let's try 6x cubed y cubed plus 45x squared y squared plus 21xy. Okay, that was a little weird. Okay. Now, if someone asks you to find the greatest common factor of that, where would you start? Well, like I just said, the easiest part is the variables. But first, I feel like I should explain what makes this difficult. Is we're not just factoring just one number by itself. We have to factor all these kind of individually, because we can't just combine them into one number because they're separated by those pesky plus signs. And because there are different amounts of the variables in each term of this polynomial we're dealing with here. So we have to figure out, just kind of in your mind, think of, wait a minute, what if you're always going to write your answer outside of a parentheses. Your greatest common factor is going to be what multiplies or distributes to all three terms. And what we're doing with the greatest common factor is we're kind of doing the reverse of the distributive property. So what do all of these terms have in common? Well, they all have x, y's, right? At least one. So let's take out one of each. So divide 6x cubed y cubed by xy. We get 6x squared y squared, because when you divide exponents, right, you subtract. So 3 minus 1 is 2. 3 minus 1 is 2. Same thing here. And that gets rid of those xy's over there on the 21 altogether. Now we're not done yet. Now it's the coefficients. The coefficients, these numbers in front of those variables, and that's a constant, but you get the picture. We need to find the greatest common factor of all of them. The largest number, let's just write that in parentheses, the largest number that divides out of all three of these, right? Well, 6, I always go for the smallest coefficient first. Whatever the smallest number is, always go there and say, can I divide them all by 6? Can you just completely get rid of that? Because 6 divided by 6 would be 1. That would be nice, right? 45 divided by 6. I don't think that comes out evenly. And definitely 6 does not go into 21. Darn. That would have been the easiest way. But okay, what are the factors of 6 then? Well, just still focused on that smallest of all the numbers. Well, we just went over 1 times 6. That didn't work out for us. What about 3 times 2? That's much more interesting. I mean, those are our only options. These are not even numbers, so 2 is out. But 3, I think we can divide all 3 of these numbers by 3. And that is our greatest common factor because it's the largest number that we can divide all 3 of the numbers by. I know 6 is larger, but we can't divide these by 6. So I'm going to have to go with 3. So let's move that 3 out like we just de-distributed it. Sounds like something a tyrannical government would do. Okay, 6 divided by 3 is 2. 45 divided by 3. 3 goes, let me just do this over here. I like doing things in my head, but my head isn't always the most reliable. 3 goes into 15. 5 times 15. Oh, okay. 3 goes into 21. 7 times. And we're done. Can't divide these by 2. If that were true, we could have just divided by 6 to begin with. So that is as simplified as that polynomial gets. And what is your greatest common factor? It's 3xy. So if you were asked to find the greatest common factor, you would say the greatest common factor of 6x cubed y cubed plus 45x squared y squared plus 21xy is 3xy. All right, let's do another complicated one. And we'll call this good to go. Well, we could check our answer there if we wanted to. Let's check our answer with this one. Sometimes you might get something crazy like this. It's probably my favorite greatest common factor because pretty much don't have to do any factoring. Now look at that for a minute. Think to yourself, what is the greatest common factor? How many terms do we have, first of all? How many terms? Well, you see, we're distributing this x, right? Because it's x times the quantity, right? And 6 times this quantity, right? But is that really 2 terms right there? Well, before I tell you what the easy, fast way to do it is, why don't we distribute everything? Actually, no. No. That'll be the next lesson. I just realized that's a couple of videos down the road. So don't distribute anything. you just have to realize and treat it like, wait a minute, I know there's a subtraction in this, but this is one number because it's in parentheses, right? So we can just think of this as one term, and this is another term. It's just two terms. What are those two terms being multiplied by? One of them is being multiplied by 6, and one of them is being multiplied by an x. But they're both being multiplied by b squared minus a. Those are the same, aren't they? Take out those coefficients. So b squared minus a plus b squared minus a, right? So they're both being multiplied by the same thing. You can actually factor that out. That is the greatest common factor right there. Just take it out, just like we did with those numbers before. This is just the opposite of the distributive property. So if somebody asks you what the greatest common factor is, well, I actually don't know which one's greater because we don't know what x is, we don't know what b is or a. So, but in this case, it was this because they both had that in common. But yeah, but no, let's actually go back to what I was saying before. Let's distribute it out. Let's actually go x times b squared and x times a. Let's just demonstrate why this works. B squared x minus ax plus 6b squared minus 6a. So what they did was they kind of found the greatest common factor of this and factored it out. And they found the greatest common factor of this and factored it out, didn't they? Let's see what happens if we kind of mix it up a bit. B squared x plus 6b squared. See, I just kind of move this over here. Minus ax minus 6a. Now we can take this part, find the greatest common factor, and take this part and find the greatest common factor. And there's a reason why I put that parentheses around this negative sign there. But first of all, let's just look at this number here. Forget about that one. Greatest common factor. They both have a b squared, right? So let's just take out that b squared. B squared x plus 6. Okay. Now look at this one. Greatest common factor. They both have an a, right? They both have a negative number. So let's just take out a negative a. And we're left with x plus 6. Wait a minute. X plus 6. X plus 6. They have a common factor, that x plus 6, right? And you think if you went back a couple minutes in this video, you will find that that was our answer. Just this was on the other side, but it actually doesn't matter because this is multiplication, right? Multiplication order doesn't matter. So it all worked out fine. Just finding the greatest common factor and de-distributing it out. Recollecting, as they could say.